Composition of compounds. The chemical formula and the molar masses of the elements in that formula give us relative quantities of each element in that compound. This is very useful practical information. One way we can express this is as the mass percent composition, or often just called the mass percent of an element in a compound. And so it's the element's percentage of the compound's total mass. This is the general form for percent. Percent is equal to the part we're interested in divided by the whole thing times 100%. And here I'm using percent as a unit. So when I left percent off on the worksheet, or it was the worksheet, people multiplied by 100 twice. And when I put the unit here, some people are going to multiply by 100 and press a percent button on their calculator, and then they'll end up multiplying by 1, and then it's the opposite problem. I can't win. Let's do an example. Acetic acid is the active ingredient in vinegar. Woohoo! Not necessary to know. Calculate the mass percent composition of oxygen in acetic acid. So if we want the mass percent composition of oxygen, so we'll call that percent oxygen. That's going to equal the mass of oxygen, grams of oxygen, divided by the grams of the whole thing, acetic acid, C2H4O2, times 100%. That's the definition of percent, right? It's the part divided by the whole. This is a mass percent, so we're looking at mass of oxygen and mass of the whole compound. They didn't give us any numbers in this problem. They didn't say, oh, it's got this much oxygen and this is the mass of acetic acid. That'd be easy, we could just plug it in. A percentage is the same. The percent oxygen in acetic acid is the same whether you have a teaspoon of it or a gallon or 10,000 gallons. The percent is always the same. So they don't actually have to specify the amount, but we need numbers. So what we're going to do is we're going to choose 1 mole. We're doing that because it's convenient. So choose 1 mole. Choose 1 mole. Can we find the mass of 1 mole of acetic acid? Yeah, we just learned how to do that, right? Okay, so for C2H4O2, the molar mass is going to be 2 times the mass of carbon, 12.01, plus 4 times the mass of hydrogen, plus 2 times the mass of oxygen, so we calculate that out. 2 times 12.01 plus 4 times 1.008 plus 2 times 16 equals. I'm getting 60.052. So that is grams per mole. So if we have 1 mole of it, it weighs 60.052 grams. So in our formula here, we're choosing 1 mole. The mass of 1 mole of acetic acid is 60.052 grams. What's the mass of oxygen in that compound? It's this right here. There are 2 moles of oxygen in 1 mole of acetic acid. So when I write this out to calculate, I've actually done the work for the numerator. So the mass of oxygen is this right here. It's 32.00 grams per mole. So grams of oxygen per mole acetic acid. So I'm going to put that number up here, 32.00 grams. And then I'm going to multiply by 100%. You see what happens to these units? Gram cancels gram. So I've got 32 divided by 60.052 times 100. And I should have 4 significant figures on this. 53.2871%, rounding 53.29%. Did I do that right? Any questions? Calculating this is not the hard part. Remembering where to get the numbers is the key to this. Pick an amount. You could pick 500 grams if you wanted. It's just going to be more difficult. If you choose 1 mole, it's very easy to calculate the mass of 1 mole and the mass of the element of interest that's in there. We can use mass percent as a conversion factor because it relates mass of an element to mass of the whole compound. So it's important to understand another way of interpreting percent. Percent literally means per 100. It's parts per 100 parts. So example, Freon 112 has this formula. And we are being told that it is 69.58% chlorine by mass. So that means we've got 69.58 grams of chlorine per 100 grams of the entire compound. This is a useful conversion factor if we had a mass of Freon and we wanted to know the mass of chlorine that was in it. Let's do an example. What mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. So 69.94% iron. We can rewrite that. That is 69.94 grams of iron per 100 grams of iron 3 oxide. You can do this problem without using the chemical formula for iron 3 oxide. I don't want to write out iron 3 oxide, so I'm going to write the formula. It's Fe2O3. This is a conversion factor. They're asking us for the mass in grams of the iron oxide. So we're trying to find grams of iron oxide, iron 3 oxide. And the starting is 58.7 grams of iron. Because they gave us this percent composition, we can just go directly from grams of iron to grams of iron 3 oxide. So 58.7 grams of iron. And I'm going to multiply by grams of iron 3 oxide. I'm going to divide by grams of iron because I want the units to work out. After I get the units in place, I look at what I wrote down as an alternate way of writing this percentage. Here I have grams of iron per 100 grams of Fe2O3. So I want to take this part, the grams of Fe2O3. My units here tell me that goes on the top. So I've got 100 up there, and the 69.94 is in the bottom. This is not the only way to solve this problem, but I think it's the most straightforward way for anyone who has gets confused by percentages, which, you know, is pretty common. So 58.7 times 100 divided by 69.94 equals, and this should have 4 significant figures, 83.9290 grams of Fe2O3. iron 3 oxide. And then rounding that and say 83.93 grams. In a percentage like this, this percentage, 69.94, that has 4 significant figures. When we write it like this, we're meaning 69.94 grams of iron per exactly 100 grams. Okay, the uncertainty comes in this number. This one's exact. So this conversion here has 4 sig figs. Oh, what did I do? I screwed up, didn't I? See that? How many sig figs here? Only 3. So I rounded it incorrectly. I don't have to do the whole thing over again. I wrote it out. See, I screw up too. So it should only have 3 significant figures, so it should stop there. So it should be 83.9. So I'm just going to erase that. There we go. Questions? We can also get conversion factors from chemical formulas. This is what we more commonly end up doing. The chemical formula has the inherent relationships between numbers of atoms and molecules or numbers of moles of atoms, numbers of moles of molecules. So this formula, C2Cl4F2, we can make 2 different conversion factors relating carbon and this compound. Is that the Freon? Yeah, that's Freon 112. So looking at this formula, C2, that tells me there are 2 moles of carbon in 1 mole of the compound. I could also do chlorine in the compound. So there's 4 moles of chlorine in 1 mole of the compound. What if I was interested in the fluorine? If I wanted moles of fluorine related to moles of that compound. Whoops. How many moles of fluorine are in 1 mole of the compound? 2. It's like right there in the formula. F2. 2 F's in 1 of those. Important to remember, the chemical formulas give us the relationship between amounts in moles, not in grams. And this is one of the reasons we always end up with moles in the middle. Because when we get down to it, it's relationships between numbers of particles. We can't count the particles directly. We have to count them by weighing. So we're always converting grams to moles. It's back and forth all the time. So determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. Well, let's see what we've got here. We're given 7.2 grams of aluminum sulfate. We might need that formula, huh? Is aluminum a metal? Yeah. So this is an ionic compound, so we have to look at the ions. Aluminum is in group 3, so it has a 3+ charge. Sulfate is SO4, 2-, because I said so. You memorize it. That's it. We look at the charges. You could do crisscross here. We end up with a formula of Al2 SO4 3. So I have 7.2 grams of Al2 SO4 3. And what are they asking me for? Determine the mass of oxygen. So I'm trying to find the mass, doesn't specify, but probably grams. I'm going to move this over. Grams of oxygen. Can I go directly from grams of the compound to grams of oxygen? No. If they gave me the percent composition, I could, but they didn't. I could calculate the percent composition and then use it. But that's going to be just as much work as going through moles. So I can convert grams of aluminum sulfate to moles of aluminum sulfate. That's just using Avogadro's number. Yeah, it gets tedious writing the formula over and over again. Just get used to it. If I had moles of oxygen, I could get to grams of oxygen. The chemical formula gives me the relationship between moles of aluminum sulfate and moles of oxygen. I still don't have enough room. Move it over. So I need to go to moles of oxygen and then to grams of oxygen. Another example of moles being in the middle. So once we have the path, we just plod through. So I start with grams of that. I'm going to change to moles of aluminum sulfate. And then I'm going to change that into moles of oxygen. Oxygen is a diatomic element, but it's part of a compound here. So we don't need to put 2's on it or anything. The diatomic business is only when it's by itself without another element. Here it's being kept company by sulfur and aluminum, so it's fine. And grams of oxygen. So grams of aluminum sulfate come down here. I'm actually going to move that over a little bit. Those cancel. Moles of Al2SO43 down there, and then moles of oxygen down here. I'm not writing the O here because it's the same as up there, and I didn't write this because it was the same. Here, when I've got the unit being the same and the substances being different, I have to write the formula. I should write the formula here, but I'm feeling lazy. So this middle part we get from the chemical formula. So how many atoms of oxygen are in one formula unit? 12. Because we have 3 of these sulfate units, and each of those has 4 oxygens. So we have a total of 12 atoms of oxygen in one formula unit, or 12 moles of oxygen in 1 mole of formula units. So 12 moles of oxygen per 1 mole of aluminum sulfate. This is the molar mass of aluminum sulfate. This is the molar mass of oxygen. I'm going to do this one first because it's a lot easier. That's 16.00. The other one I have to calculate. 2 times 26.98. How many sulfurs are in there? Well, I wrote this one wrong. This here is supposed to be a 3. There's 3 sulfurs, right? In 1 mole of aluminum sulfate, 3 moles of sulfur. So sulfur is 32.07. And then there's 12 oxygens, and they are each 16.00. 2 times 26.98 plus 3 times 32.07 plus, I lost, 12 times 16. 342, wow, that's big. It's okay. It is what it is. 342.17. And that's grams of aluminum sulfate per mole of aluminum sulfate. So that's the number I need over here. 342.17. So 7.2 divided by 342.17 times 12 times 16. This should have 2 significant figures, so I'm going to write the first 2. Come on, I need a decimal point there. And then 2 more, 40, grams of oxygen. You guys getting the same number?
Where did you get the number from?
The what?
4.0.
I'm multiplying all of this out.
Oh.
So 4.0 grams of oxygen. It is very easy to make a mistake when you do a long calculation like that. Some calculators you can look and see what you did, so you can just look back and compare and make sure that you typed them in correctly. Or just clear it and type it in again. If you get the same answer, it's probably correct. If you're making a mistake, it's probably going to be random, and the second time you do it, it will be different. So if you end up with 2 different answers, do it a third time and go with best 2 out of 3. If you get a third different answer, you need to slow down and be more careful. Any questions?